This lesson is on empirical formulas and molecular formulas. Empirical formulas provide the simplest whole number ratio between atoms in a chemical formula. Molecular formulas provide the actual number of atoms per element in a chemical formula. Examples include CH, which is the empirical formula of the molecular formula C2H2. A second example is CH2O, which is the empirical form of the molecular formula C6H12O6. Third example is HO, which is the empirical formula of the molecular formula H2O2. In a word problem, if you're asked to find the empirical form of a substance, sometimes you'll be given the amount of each element as a mass percentage, and other cases by mass per element. The keys to solving empirical formulas starts by checking the following. 1, the total percentage of all elements is equal to 100%, or 2, making sure that the total mass of all elements equals the total mass of the compound. If not, normalize the masses by finding the mass percent of each element by using the following formula. Percent of X equals the mass of element X divided by the total mass of all elements times 100%. The solution map shown here provides a path into solving empirical formulas using the following steps. Take the mass percent of each element and assume that there are 100 grams of the sample. Then express the percentages as the mass of each element in grams. Take the mass of each element and divide by the atomic mass of each element to acquire the moles of each element. Create the pseudo form by taking each element's amount in moles and divide by its lowest amount in moles to eventually determine the empirical formula of the compound. It is handy to have a periodic table and a scientific calculator necessary in performing these calculations. When dividing the amounts of each element by the lowest amount, it is possible that a whole number integer per element will not happen. In this case, you will have to seek out and multiply all amounts by a common coefficient to result in whole number subscripts. This table below provides the possible fractional subscripts and the multiplication factor needed to acquire a whole number integer. If the problem involves determining the molecular formula, then the problem must have present the empirical mass of the empirical formula, either determined in the problem or given in the problem. With the molar mass of the compound provided in the problem, one needs to determine the mole ratio between formulas, where one can compute this value n by taking the molar mass and divide it over the empirical mass. The value of n is usually a whole number integer. Let's begin with problem 1. A compound contains 29.1% sodium, 40.5% sulfur, and 30.4% oxygen. What is its empirical formula? Pause the video if you'd like to try the problem. Continue when ready. The solution starts by first expressing the percentage of each element as masses. The result is that there are 29.1 grams of sodium, 40.5 grams of sulfur, and 30.4 grams of oxygen. Next, determination of the number of moles of each element is performed. There are 1.27 moles of sodium from 29.1 grams of sodium, 1.26 moles of sulfur from 40.5 grams of sulfur, and 1.90 moles of oxygen from 30.4 grams of oxygen. Now, finding the pseudoform of the empirical formula is done by writing the elements from most metallic to most non-metallic. The lowest amount in moles was 1.26, and once dividing all of the elements moles by 1.26, the empirical formula is NaSO 1.5. However, since the empirical formula has to be whole numbers, a multiplication factor for each subscript was done by a factor of 2, resulting in a final empirical formula of Na2S2O3. Problem 2 is as follows. Mannose is a sugar which contains only carbon, hydrogen, and oxygen and has a molecular weight of 180. A 2.36 gram sample of mannose was found on analysis to contain 0.944 grams of carbon and 0.158 grams of hydrogen. Determine the molecular formula. Pause the video if you'd like to try the problem. Continue when ready. First, we need the mass of oxygen because the substance contains carbon, hydrogen, and oxygen atoms. Since the total mass of the compound equals the sum of masses of carbon, hydrogen, and oxygen atoms, the result is that there are 1.258 grams of oxygen present. Next, determination of the number of moles of each element is performed. There are 0.0786 moles of carbon from 0.944 grams of carbon, 0.157 moles of hydrogen from 0.158 grams of hydrogen, and 0.07863 moles of oxygen from 1.258 grams of oxygen. Now, finding the pseudo formula of the empirical formula is done by writing the elements from most metallic to most non-metallic. The lowest amount in moles was 0.786, and once dividing all the elements moles by 0.786, the empirical formula is CH2O. Next, finding the empirical mass of the empirical formula is done by adding the atomic mass of C, H, and O, respectively, in terms of grams per mole. The atomic masses are 12.01 grams per mole for carbon, 1.008 grams per mole for hydrogen, and 16 grams per mole for oxygen, for an empirical mass of 30.036 grams. Next, find the mole ratio between the molecular formula and the empirical formula. The molar mass of the compound is 180 grams. N equals 180 grams divided by 30.036 grams for a final value of 6. Thus, determining the final molecular formula is done by taking the empirical formula of CH2O times 6 for a final molecular formula of C6H12O6. Problem 3 is as follows. A compound was found to contain 65.4% carbon, 9.15% hydrogen, and 25.4% nitrogen. Its molecular weight was found to be 220. Determine the molecular formula of the compound. Pause the video if you'd like to try the problem. Continue when ready. The solution starts by first expressing the percentage of each element as masses. The result is that there are 65.4 grams of carbon, 9.15 grams of hydrogen, and 25.4 grams of nitrogen. Next, determination of the number of moles of each element is performed. There are 5.45 moles of carbon from 65.4 grams of carbon, 9.08 moles of hydrogen from 9.15 grams of hydrogen, and 1.81 moles of nitrogen from 25.4 grams of nitrogen. Finding the pseudo form of the empirical form is done by writing the elements from most metallic to most non-metallic. The lowest amount in moles was 1.81, and once dividing all the elements' moles by 1.81, the empirical formula is C3H5N. Next, finding the empirical mass of the empirical formula is done by adding the atomic masses of carbon, hydrogen, and nitrogen respectively in terms of grams per mole. The atomic masses are 12.01 grams per mole for carbon, 1.008 grams per mole for hydrogen, and 14.01 grams per mole for nitrogen, for an empirical mass of 55.08 grams. Next, finding the mole ratio between the molecular formula and the empirical formula is done. Since the molar mass of the compound is 220 grams, N equals 220 grams divided by 55.08 grams for a final value of 4. Thus, determining the final molecular formula is done by taking the empirical formula of C3H5N times 4 for a final molecular form of C12H20N4. Problem 4 is as follows. A compound was found to have the empirical formula of CH2 and a molecular weight of 71. Determine the molecular formula. Pause the video if you'd like to try the problem. Continue when ready. First, finding the empirical mass of the empirical formula is done by adding the atomic mass of carbon and hydrogen respectively. The atomic masses are 12.01 grams per mole for carbon and 1.008 grams per mole for hydrogen for an empirical formula mass of 14.036 grams. Next, finding the mole ratio between the molecular formula and the empirical formula. And thus, the molar mass of the compound is 71 grams. N equals 71 grams divided by 14.036 grams for a final value of 5. Thus, determining the final molecular formula is done by taking the empirical formula of CH2 times 5 for a final molecular formula of C5H10. Here are a couple of additional problems as exercises for you to try. One, a sample of 2.12 grams of copper was heated in oxygen until no further change took place. The resulting oxide had a mass of 2.65 grams. Determine the empirical formula of the oxide. Two, a pure compound was found on analysis to contain 31.9% potassium, 28.9% chlorine, and 39.2% oxygen. Determine the empirical formula. Pause the video if you'd like to try the problem. Continue when ready. For the remaining part of this lecture are solutions to review exercises or problems. Please view only after completing these exercises.